Thanks for coming along, and it's my pleasure to introduce this particular program to you. Now, I do apologise for my lack of technical knowledge on using Zoom, but we'll see how we get through the evening. So, look, tonight is all about introducing the ATU, and there, as I look around the room, we have very much a mixed audience. We've got some old and bold, some not so old and not so bold, and all combinations in between. So this presentation is not about getting into the absolute technical detail of everything, but I hope to be able to give you enough of an understanding to understand what it is we're building, how to use it, and also to give you an overview of the project, what to expect. And remember, the most important thing out of the whole lot is to have some fun, and I'm sure we will, just as we have with the other projects. So first of all, we're going to introduce what is an antenna tuning unit. Now, in essence, when you boil it down, it's simply an electronic device that gets inserted between, or a device that involves electronics that sits between your radio and the antenna. Its purpose is to optimize the flow of power from between the two. I mean, you can use an antenna tuner for a receiver as well, so it'll optimize the receiving signal going into the antenna, just into the radio, just as much as it will optimize the power coming out of the radio into the transmission line and ultimately up to the antenna. It's often described, and I think the simplest way to think of it is as a combination of variable inductors and capacitors that will enable you to effectively match the impedance of your antenna and its transmission line to the output impedance of the radio. Why would you want to do that? What's the benefit of doing that? Fundamentally, the basic purpose is to ensure that the antenna's impedance matches that of the radio to facilitate the maximum transfer of power. Now, the important thing to remember here is that whatever you do with an ATU, it is not going to change the radiation efficiency of your antenna. Okay, if you want to tune it, perhaps an ATU is the wrong name to use. It's not an antenna tuning unit. It's actually, for want of good, a transmission line matching unit, or a matching unit, if you will. The antenna itself, its radiation efficiency and its effectiveness is really going to depend upon the antenna design and how well the antenna itself is tuned in terms of the length. So you're not going to magically change that, but you do have some advantages as we go through. So this page is for Bill, because Bill, being the technician that he is and the very complicated and capable man there, he wouldn't let me go home if I didn't put up a fancy, complicated set of equations and formulas up there, which he's going to pore over with intently as we watch this particular slide. But look, the reality is that the antenna tuner is, as I said before, it's a network of variable inductors and capacitors with the aim of effectively matching your antenna system to your radio. The theory is complex. It really is, and if ever you want to realize just how ineffective you are in terms of your knowledge, start delving into the depths of transmission line theory and start working it out from scratch. But the reality is we can simplify it. For all intensive purposes, as far as hams are concerned, you don't necessarily need to involve yourself with the theory unless you want to start getting into the design, but you need to understand what it is that you're trying to do with an antenna tuning unit. And that's hopefully what I'm going to try and explain this evening. We're going to use a Smith chart and the demonstration of the use of the antenna unit on a Smith chart to try and explain to you how that impedance match works. And a Smith chart actually plots a complex reactance. Now, what's a complex reactance? In essence, once you get a phase difference across a component between the voltage and the current, you start to get a complex reactance occurring. The point that I'm trying to make here is that the ideal situation where you're going to get an ideal match is when you have a resistive load rather than a reactive load. So what you try to do is to match, or is to adjust let's call it the antenna. And by antenna, I mean the antenna and the feed line, or whatever is the connection point, so that the inductive reactance equals the capacitive reactance, and the effective, you get a purely resistive load. And if you can see on here, if I can move my mouse, which I can, my mouse is occurring up here. This is a Smith chart. I've got a larger picture of one coming up on the next slide, but basically The reactance of a circuit when you put a particular frequency in will be either capacitive, inductive, or resistive when the two of them equal out. And that single point is plotted on a Smith chart. There's all sorts of computations that actually happen. You put a frequency in it, it'll plot a single point. And that point will indicate, let me just go back here. It's a bit confusing because I can't see my mouse on this screen. That's okay. So the way the Smith chart works is this line that's running across the middle here is the resistive line, if you will. You go up, if the plot occurs above the line, it's inductive. If it occurs below the line, it's capacitive. So you try and balance things out so that a purely resistive load here at 50 ohms. So this line across here, this is 0 ohms, this is 50, this is an infinite amount of resistance on the way through. So we've got a great video coming up in a moment to actually explain that. But what I wanted to show here was that this, you may have seen this happening here. You see this line that's coming through there. That's actually a sweep. It's a scan between two frequencies in which it's plotting the complex reactance at each of those particular frequencies that goes along. And you'll see that occurring on the next slide. So let's just have a look here. What I wanted to show here is that he's going to use an example where he has a screen which has a Smith chart that looks like that. And it's actually missing the straight line that runs across here. I'll talk to it. I think if my build works correctly, there we go. So I've superimposed the yellow line across there, which is the line of purely resistive load. And then when he does the first plot, you'll see that his the point that he shows is sitting up here. And the idea is that he'll adjust the capacitance and the reactance in his tuner to bring that point down to the perfect match, which is actually at 50 ohms for that particular system, where it's a purely resistive load. And that's what the antenna tuner is doing.
Fun from the shack here this evening to show how you can visualize the operation of an antenna tuner like this one here by using a vector network analyzer and setting it up with a couple of displays, each of which will show you the operation in a slightly different way. Well, normally when you use an antenna tuner like this, you're tuning up at a particular frequency. So we're going to do the same thing with the VNA. We'll set it up in 0 span, in this case at 7.2 megahertz. Now the analyzer is set up with 3 displays, but each display is really just measuring S11, the reflection coefficient, but it's displaying it in 3 different formats. Down here in the lower right corner is the traditional logarithmic magnitude of the S11, but again, we're in 0 span, so we're going to have a flat line. The reflection coefficient is also expressed as the standing wave ratio, or SWR, which is the most common thing that hams will look at. So I displayed that here as well. And then thirdly, we're also displaying the reflection coefficient as the complex impedance looking into the coax. So this is what the transmitter would see on the Smith chart here. Now, the Smith chart is just quickly a way of displaying a complex number, in this case, complex impedance, where we have essentially circles that represent constant resistance, and we've got arcs that represent constant reactance, both inductive and capacitive reactance. And the location of where you are on the chart tells you essentially the complex impedance. So right now, before we start adjusting the tuner, we've got our marker sitting right at our single point at 7.2 megahertz, and that's giving us a input impedance looking into the coax of 20 ohms plus J 38 ohms, so an inductive 38 ohms and a real part of 20 ohms, and that's what that point represents. Now if I reach up and grab the capacitor control on the tuner, I can see a couple of things. I can move the impedance that's seen on the Smith chart,
Moving it backwards and forwards,
kind of on an arc as we adjust that capacitor. I can also see the return loss and SWR curves moving as well. If I grab the roller inductor of the tuner and start adjusting that, I can actually see myself moving along on the Smith chart as well as the other displays. Now our goal is to get a 1-to-1 SWR, which will be achieved when the input impedance is right here in the center of the chart, right at 50 ohms resistive. So all we need to do is essentially adjust our controls to kind of get us there. And you can see I adjust my inductor down, my capacitor back here, and get ourselves really close. We're really careful here and zero in to something very, very close to just a 50 ohm resistive termination. And if we look here now, I'm at 49.7 ohms and about 0.4 ohms of inductive reactance. And if we tweak that a little bit more, I might be able to get even closer. Okay. And with our cells very closely centered here, we take a look at our SWR plot, and we're sitting at 1.008 to 1, and our return loss is 47 dB. So we've achieved a really, really good match by simply tuning the capacitor inductor on the tuner and visualize that a couple of different ways. Well, now that I've tuned up at my desired frequency of 7.2, I've changed the VNA to give me a span of 400 kilohertz. So now we'll sweep from 7 meg to 7.4 megahertz, which more than covers the 40 meter amateur radio band. Now, of course, on the Smith chart, I can see the input impedance to my antenna system. Now, what I mean by that is the antenna, the tuner, and the coax leading to the transmitter. And this is what that impedance looks like over frequency. And if I can drag that marker around and actually see what that impedance looks like at any frequency within that sweep, going back and forth. Okay. Of interest to most hams would probably be this plot right here, which is showing me my standing wave ratio, or SWR, versus frequency. I've actually put a pair of markers here at the 2-to-1 SWR points. And this indicates that I've got something in the neighborhood of about 140 kilohertz of 2-to-1 SWR bandwidth. So covering, not quite half of the 40 meter amateur radio band. And of course, of interest to most RF engineers would probably be just the log magnitude of the reflection coefficient, which is shown down here. But all of these are essentially the same measurement, just displayed a couple of different ways. And today's video was basically just for fun, but I do plan on doing some more tutorials on the use of VNA for various applications in the future, as well as maybe even some tutorials on the Smith chart itself. An old tool that RF engineers have used for many years, but maybe a bit of a lost art these days in terms of how you can actually use it manually. So maybe we'll cover that in some future videos as well. Anyway, if you like what you see, give me a thumbs up if you haven't subscribed already.
Look, that was a great video to my mind. It's one of the most succinct ones. You can really see the impact of that happening. I had actually planned to do that myself here on the screen this evening, but I took my Nano VNA back to Sydney with me, and I still left it back there, so I didn't have it. But I think that was probably much better than I could have done in terms of the display. Great results can be achieved with the humble Nano VNA. I use, you saw me using the VNA here when we're looking to tune the parallel circuit. You can pick them up from, shall we say, a Chinese copy of one for about $60. If you want to buy them here, they're about 100, which size of the screen you get. But quite honestly, because you can also use it for tuning antennas, looking at tuned circuits, there's a whole range of stuff you can do. It's probably one of the most practical pieces of kit you could have in your ham shack. So I would recommend that you do that. This is what I was talking about with the sweep, where you can really utilize that sweep to actually tune your antenna. But you'll see, you actually don't need to have a VNA to get the ATU working properly as we work our way through. Now, it would be remiss of me not to at least talk about the different types of antenna matching networks. And you can rest easy. I saw you go into a panic there, Bill, but you don't need to worry about it. We're not going to go into the theory of each of those. I think it's important just to know, for all practical purposes, that ATUs often involve a combination of variable capacitors and inductors arranged in various configurations. Each of them has their strengths and their weaknesses. If you want to look it up, by the way, this PowerPoint presentation will be on the Cowtown Group's IO site. It's also on my GitHub, along with the other documentation and stuff for this material. So you'll be able to go there and have a look at it, pull it down if you want. This It's probably too small. I can't even read where. Oh, it's on the top there. Look, sorry, you can't see it. Here you can. On the top, there's the reference to that, which gives a pretty good description of the advantages and disadvantages of each of the types of networks. If you look at the top left-hand corner there, the Pi network, that basically has a variable inductor in the middle and a couple of variable capacitors. You can have a symmetrical Pi network, which swaps it around. Each has advantages and disadvantages. The L network is probably the most simple of the lot. That's simply an inductor and a capacitor. The advantage of that is that whilst it has some disadvantages, it's got a very low power loss due to the heating of the components as it works its way through the ATU. That's probably why that Tentec that you just saw the guy using, that's rated at 2 kilowatts, and that uses that particular type of network arrangement. We'll talk a little bit about the T-match in a moment, but also the Z-match is a very popular one for QRP operators. You can see those, you can buy those on the net. They have simply has a fixed inductor, and you vary the capacitance, as you can see in the circuit over here. It's a dual, there's 2 capacitors, but they're actually dual capacitors in a gang, so when you turn it, both of them turn at the same time. That is fairly easy from the point of view of its ability to tune, because you've only got to use 2, you don't have to select the inductor and then tune the 2 capacitors. But the reality is tuning is usually very narrow, and it's a little bit touchy, so it's very difficult to get that absolute perfect max with the Z-max, or the Z-match I should say, and the range of impedances that it can match is not as good as you would find in the T-match ATU. Hence, as we go forward, the advantage of the design that we chose for the Cowtown project. Now, this particular type of network involves 2 capacitors and a variable inductor. Now, that inductor can either be a tapped inductance, which is going to give you a series of set values around which you adjust the capacitance, or if you want to get the truly perfect match, you would actually have a T-match with a variable inductor as well as the variable capacitors to be able to optimize your the resonant point. This particular design is the one that we've used. It's the one that's most commonly used in all of the commercial ATUs that you would go out and buy that's out there. Got a good range of matching capabilities. It's just effective. If you look at the Pi there, it's actually an L network reflected on its side. It's almost L networks sharing a common inductor if you were running through the middle. Because you've also got a capacitor on the input side as well as the output side, it gives you a great opportunity to actually balance 50 ohms on both the transmitter and the receiver as when you're looking at coax on the way through. The design that we've got, and I think that yes, the next slide outlines it. Let's just talk a little bit about the circuit diagram in the Cowtown kit. Comprises 3 fundamental zones, if you will, within the kit. So the circuit itself is divided into 3 zones, the way we constructed it here. The first is the switching area, which is shown in green on this particular chart here. So what we've done, we've installed a bypass switch up the front, and its purpose is to simply select whether the RF signal or the RF path, if you will, bypasses the whole ATU and goes straight through to the other end, effectively having the ATU completely switched out of circuit. So you put that into play. That is, you switch the, looking around here, that's the ATU switch here, switch basically ATU bypass or into the ATU. When you switch the ATU in, you have the option via this switch here as to whether you either engage the SWR indicator or you don't. Now, the SWR indicator, which is the salmon-coloured section down through here, involves basically a resistive Wheatstone bridge as the SWR sensor. Effectively, when the antenna impedance is exactly 50, it's matching the Wheatstone bridge there, it's in balance and no voltage is going to flow across the input side of the transformer here, or the inductor, which is actually a transformer. So, but when you move away from the 50 ohms, you start to get a voltage developed across this particular, these coils here, which then on a 2 to 5 transformer steps up the voltage and activates and illuminates the LED, indicating that you don't have a perfect match. So you're adjusting the ATU component, which is the last section here. which is the T-match network that we described before with the two, actually the next one there's the circuit diagram for the T-match network, and you see that sitting over here, the two capacitors and the variable inductor, in which case it's a tapped inductor with 12 taps. So when you adjust this here, when you hit the perfect 50 ohms on the way through, no voltage flows through the LED and it extinguishes. Now, the reality is that by switching that in, you introduce a 6 dB loss to the signal path, so that once you've got it tuned, you disengage it and effectively bypass that so you don't suffer that loss as it's working its way through the antenna. It's about as simple as it comes, but it's a very effective on the way through. In terms of where do we stick the ATU in the antenna path or in the antenna system, assuming you have a 50 ohm coax connected to a 50 ohm loaded PA on your transmitter, which is what it's looking for, the ideal location would be to site the ATU right at the end of the transmission line when it's going into the antenna. Now, for most people, that's not very practical. It's going to be a bit hard to climb the tree each time you want to tune the antenna. So we site the ATU down next to the radio down the bottom. Now, the point that I'm making here is that it is a common misconception that the high standing wave ratio causes losses. Well, that's not actually true. The high standing wave ratio exists as a result of the power being reflected back from the antenna system, if you will. And when it comes back to the ATU, it just gets reflected back up the other end again, because the ATU is protecting, for want of a better word, the radio from SWR coming back. For those of you that built the ADX, you'll find that if you don't have a perfect match with many of the QRP radios, if you don't have a perfect match on your antenna system, the reflected power going back into the radio will start to overheat your power amplifier section fairly easily, because there isn't any protective mechanisms that are in there, and it will get hot. So the ideal is not to do that, and that's where the ATU really comes into play. The example that I showed here is that if you have a 2-to-1 SWR, and by the way, I always try and strive for an SWR of 1.1 or thereabouts if I can. I mean, I always try and get all my antenna systems down at that particular level. But with an SWR of 2, 11% of the power is being reflected. So only 89% of it is going out. Well, if you're able to do better than that and effectively increase the power that's going into the antenna system by that 11%, you're going to get 89% of that 11% radiated on the other end, because it's going to go backwards and forwards. So effectively, if you're at 100 watts in and you're only effectively able to transmit because of the PA closing down or whatever's going on, you can't get as much power into the antenna as you can. The more power you can get in, irrespective of what the actual SWR on the antenna is, the more you're going to radiate. Does that make sense? Okay, and you protect your radio at the same time. Now, the point that I'm making here down here as well, that it's worth placing an SWR meter in line with the actual, as close as you can to the transmitter, to actually monitor what's going up and down the system as well. But really, it's often not necessary, because most modern radios these days have an SWR indicator on them, which you can monitor while you're transmitting. Or if you're concerned about it in this situation, just flick your ATU across to SWR. Just check that you don't have the LED illuminating, and flick it back again if you want to check from time to time as you go forward. Now, when you read the literature, there's all sorts of SWR meters, ATUs available, and they broadly fit into 2 categories, and I've actually split them into 3 here. The first 2 types, left to right, are in fact the manual ATUs, which are exactly the same that we're building here with the Cowtown kit. And in fact, this one here is effectively both of these. You can see here, all you've got here at the front end is an SWR indicator. By the way, in this case, a cross needle SWR. You have an antenna selection switch, so you can actually select which antenna you go to, whether you direct into bypass or through the ATU or into a dummy load. And then you have a central tapped inductor and 2 variable capacitors each side. If you pull the top off, in this case here, the actual tapped inductor is a fairly large inductive coil sitting there, and the 2 capacitors are actually tucked away either side of that. You can't quite see it over the lid. This one here is the one with the roller inductor that I used in the video. If you've seen the video about the project, that's the actual unit that I was using there. And sitting inside that, here you have a large roller inductor, and then sitting there's the two capacitors, either side of it sitting there. And again, just an antenna selector switch and a method of displaying the SWR. So there's nothing really magic about these things. It's the same principles, just on a larger scale with components that are capable of handling more power. We start to get into automatic antenna tuners. They simply have a microprocessor which is monitoring the what's going on in the tuner, and then using a series of relays switches in capacitance or inductance to be able to bring let's just say we bring the SWR down to that minimum point, if you will, and it will oscillate backwards and forwards. You'll hear it go as it switches the relays backwards and forwards to be able to find that optimum point. Now, so just to give you an idea of what these sort of things cost, if you want to buy new, these things are about $215. These are about just under $300. This particular here one's about $300 itself. This one here is an ATU 100. You can buy them fully built from China for about $60, or you can build one yourself. I've got a kit sitting at home waiting for me to find some spare time. That was about $17. I'm going to put that in as an automatic ATU inside my Microbit X, so that I'll have an ATU capability in that. The Z tuner that I spoke about before, they're about $30 from China if you want to buy and bring one of those in. And some of you may have seen this. This is the little automatic antenna tuner that I have, which is quite expensive, but this thing has latching relays, so that once it's set, it basically switches off, so there's no need for to maintain any power to the ATU. So fantastic for QRP operations when you go out and you try to run off batteries. Your thing turns on, tune the antenna, switches off, no power consumption.
Which one has the latching relay?
This one, the ATU 10. Yep. I'd also show you that as well, but that's sitting in Sydney right now on the way through. No. You might want to talk to Mike about that, but he might have trouble getting on board. But look, that gives you an idea of the range of ones that are out there. And I'm sure halfway through the build, you're going to wish you spent the $30 and bought the Z Match, because particularly if you're having to rewind the toroid for the fourth time. But anyway, a lot of fun. So let's talk about the Buildathon and what we set out to do and where this all fits into the process. The reality is, this is the third project in the series. We set out to have some equipment that was practical and we could actually use out in the field. Now, those that have built and operated the NFET half-wave will probably swear black and blue by its effectiveness and how great a little antenna it is for what, a couple of bucks is really what it cost to put that together. The ADX, I just love that ADX. I've used it extensively, and those that have, it's such and the fact that you can sit there and play with it. Now, I built that. It works. I built this radio, and it's two ways. Is a great way to go forward. The QRP ATU that we're about to build complements all three of those. So you can put that, if you want, between your ADX and your NFET half-wave, or whatever you wish to do. But we've effectively almost got a complete working system, if you will, antenna, transceiver, and an ATU on the way through. But importantly, what we tried to do with the Buildathon was introduce people that weren't used to building things to various techniques and construction techniques to give them some confidence in building sort of stuff themselves and going on and trying other projects and so on as we go forward. Now, the project here, it introduces a few things. There's a few things that are different about this one. There's a lot of hardware mounting and integration and mechanical work. The emphasis is here on mechanical assembly and construction as opposed to electrical assembly with the stuff before. And as a ham, you often find yourself, particularly if you like doing this kind of stuff, building all sorts of bits and pieces to solve a problem. And this is a great introduction to that. You've all seen it. It's sitting here, but let's have a look at what we need to go through in the thing in a bit more detail. This itself, the limiting factor, but the primarily limiting factor in terms of the power handling capability of this are the polyvariacon capacitors that are in there. There's a thin film of polyvinyl ethylene chloride or something, whatever it is, sitting between each of the plates on the capacitor. If you put too much power in, too much voltage, you're going to arc out between the two plates of the capacitor. It'll burn a hole in the through the dielectric, for want of a better word, and the net result is that you'll burn out your capacitor, bottom line. That's the bad news. The good news, if you do that, they're less than $1 each. You know, they're very easily obtainable. You can buy them in a pack of 10 for $5 or something. I can't remember exactly what it is, but they're very inexpensive to replace if you need to do so. So the reality is you're going to be running about 10 watts sideband max, probably 5 watts if you're running CW or digital through these things to work effectively. But for what we're doing for QRP, it's an ideal way to do it. Use the T-match, as we said before. The SWR meter, the little LED here works really well. I was surprised at just how accurate and how illustrative it is in the way you do it. And again, if you watch the video, you can see me tuning up. By the way, on that video, you saw me only moving one of the capacitors with one hand. That's because I was trying to key down the ADX with the other and not knock the camera that was doing it. You do actually need to adjust both capacitors to try and align it and bring it into the area there. But we'll talk a little bit about that as we go forward. The Cowtown kit, however, does have a few extra features above and beyond the standard Chinese kit that we bought here. And a lot of the learnings for this in terms of what we needed to do differently came from this excellent video that Carol KP4MD put together, where she was looking for a project for their particular club. They looked at a whole range of different QRP ATUs in kits. They ranged in price from $15 as this one up to about $50 for some of the Z-match ones, depending what you're doing. And this kit, I indicated in some of I think it's in the preamble in here, it's quite well maligned, justifiably so, on some of the YouTube videos and so forth that you see around, because the instructions that come with it and the circuit layout is actually wrong. And she explains what is wrong with it, but fundamentally, the inductor is shown back to front, so the minimum inductance is actually the maximum inductance. The windings on the transformer on the drive the LED are back to front, and they're also labelled back to front on the little PCB. The knobs that you put on there to try and tune the variable capacitor are an absolute nightmare. I don't know why they just don't fix it and get that right. But no, we fixed all of it. Something happened. Maybe it was just with it. That was just.
I think somebody left.
Oh, somebody left. Okay, sorry. So anyway, we fixed all the issues with that, and the reality is this is actually a very practical piece of kit as we work our way forward. So what are the differences? What I've tried to do here is illustrate what those differences are between the base kit that you can get off Amazon or wherever and what we have. So fundamentally, I've redesigned the front panel. So clearly you can all see the front panel there. You'll have seen that see it quite clearly up there. So there are a couple of front panel decals that I've got there. I redesigned that, printed them out, tweaked around as to what actually works. The nice thing about this is you've actually got a little table up the top right-hand corner here, which gives you the starting position of the inductor when you're trying to tune. So whichever band you're looking for, you look for that. You turn the inductor switch to that particular setting, then you start trying tuning. If you don't tune, you then go to the next one up or the next one down to work your way along. I indicated in here that in the manual there is actually a guide as to how to use it to tune. If you're using on the same antenna, it's a good idea once you've tuned a frequency to actually write down the numbers and the letters for hence why it's labeled. So you write 3.5 D 2.5 or whatever it is for a particular frequency, so you can always go back to that, and it speeds the tuning process very quickly. I redesigned the drilling template because the original drilling template didn't work. So if you drilled the template using the drill that was there, you got interference between some of the components and also with in the housing itself. So that's been redesigned, and I know you guys struggle with millimeters. I know, I feel for you, and I lost sleep for 4 days after I put this together. And in the end, I went back and rewrote the drilling template and put imperial measurements on there, just for my American friends. So there's both. So there's millimeters and freedom measures on the way through. The other thing that I did was I spent a lot of time trying to work out how the hell to fix up this this knob cost effectively, because believe it or not, that little pack of knobs that you've got, the extra bits and pieces, that's worth about half as much as the rest of the kit put together. Anyway, cut a long story short, after a lot of research and poring through things, I basically found a solution, and I'll talk to that in a few moments. So we've got a whole set of knobs. Also, you've got some different magnet wire to wind the toroid with, or the tapped inductor. The stuff they've provided in the kit is, I think it's 18 gauge. Good luck winding 18 gauge around a tiny little inductor like that 36 times and putting 12 taps on. If you want to do it, be my guest. You're better off putting that to one side and using that for a high-powered unun for an end-fed half wave. You can run 100 watts through the thing with 18 gauge. We're only running 5 watts, so I've included in there some beautiful, easily malleable 22 gauge wire, and it also has lower temperature enamelon, thank you. So it's easy to scrape off, and if all hell breaks loose, just hold your soldering iron on a bit longer and likely burn off, and you'll get a good connector on the way through. And as I said, drilling template, and the piece de resistance is, of course, this beautiful construction manual, which I put together when I built my first, the first one, built this guy, and I'm hopeful that you'll get a lot of strength out of that, a lot of courage. You'll be sick to tired of reading all the words in it because it gets a bit verbose in spots. But remember, I've tried to do that for somebody that's never done this before, to try and talk their way through it on the way through. Now, out of the goodness of my heart, I agreed to build Anthony's ATU last weekend, and I thought, okay, here we go again. And so I sat down to do it, and I discovered a couple of things that I thought would make it a little bit easier. So I rewrote sections of the manual, but I'd already published the ones that everybody's got here. So as not to, and I'll cover that in a minute, but anyway, you've got the extra bits that I've printed them off, and they're included in the back of the manual. There are some loose leaf pages on the way through. You know, when you come to build it, there are actually, I describe it as 6 different steps of construction, and you can do each one except the last 2 independently. And the first bit is actually constructing the circuit board, which has got the SWR indicator, which has the Wheatstone bridge in it. You'll notice here that the switch and the LED are not installed. So if you're not coming along to the Buildathon session on Saturday, when you build this, do not solder the switch and the LED in until you come to fit it in the box. I say that very clearly and very explicitly in the instructions. Trust me, don't ask me how I know. If you happen to solder the switch in before you put the LED in and you try to fit it in the thing, be prepared to dedicate 30 minutes of your life trying to get it to fit. So it's much easier to do it this way, and you actually it explains it all in the manual here. Winding the tapped inductor here is, if you just go at it cold, it's probably the most challenging thing to wrap your mind around, because you not only have to wind it, but you've also got to make sure you wind it in the right direction so that when you turn it upside down and put it on the back of the switch position indicator is correctly aligned with the taps that you've got on the inductor. If you do it the wrong way and you get 2 or 3 winds into it and you realize it's the wrong way, you've got to undo it and start again and try to do it the other way. Don't ask me how I know. And you know, it does take a while. Fortunately, there's a fool's guide as to how to do it the right way first time on here, and that's in the manual. So hopefully you'll be able to
Did everybody get that, or just mine?
I'm sorry?
Did everybody get that, or just mine?
Everybody's got that.
Oh, really?
Everybody got that. Now, the switch itself, Bill, I wouldn't be able to sleep at night if you weren't able to do that. This is the finished product, and you know, look, I just pass it around and just ooze quietly as it passes by.
Nobody put it in their pocket.
You know, when you built that, you look at that, and by the way, when you wind the toroid, and the reason I'm telling you, because some people are not going to be here on Saturday, when you wind the toroid, you've kind of got to then spread it out equally around to fit around the lugs on the back of the switch. Don't stress about it, because as you put the lugs on, you solder them on lug by lug by lug, and as you do that, you're able to move the taps around, and it becomes more evenly spaced. So it becomes quite easy to do in the rest of it. But if you're like me, after you spend what seems to be like hour after hour trying to get that thing constructed, you put it back. You don't even want to touch it. You want to put a floodlight on it, shower, put it up on a top shelf, and sit there and stare at it for hours on end. It's an absolute piece of art on the way through. But anyway, you build that to you can do that as a project. You say, like, tonight I'm going to build the tapped inductor, and away you go. So you can break it down into stages as you work your way through. The next challenge here is drilling the housing. Now, that's a common look. The fact that you've got a drilling template and everything's already organised out for you, and you've got the overlay to go on top. I'm going to say you can't go wrong, but you probably will if you don't pay attention to what's actually happening.
I was going to say you can't go wrong. You haven't seen me with the drill press.
And you've got your challenges these days, I know, Bill. But the one thing that I did notice, this is the first kit that I bought when I put this together. The housing for this is actually a much tougher housing than the one that was supplied with the batch of 20 that I brought in from in one hit. So this is a little bit more brittle than this. So don't go putting massive amounts of pressure on the thing. You may well crack it. Just let the drill do its work on the way through.
Richard, what did you use to mark the drill? Was that a center punch?
Watch this space. I'm just about to show you that.
Right.
So yeah, something far more sophisticated than a center punch. And then the next phase, of course, is just assembling the components in. You can see I've got them ready on this one. By all means, come up and have a look at in the midst of construction. But that's all explained in the guide as we work out forward. And then finally, putting it all together and making it look as pretty as punch with the overlay and working its way through. As I said, drill templates there. We also have the panel overlays. Now, what I'm showing you down the bottom there is that, actually, I'll probably just use the screen rather than trying to do here. It doesn't matter when you're cutting out the holes that need to go on the overlay, whether you just do two tiny little holes either side for the two little screws that need to go down into the polyvericon, or you cut a larger hole, as I'm showing you here. I've used both techniques, because the reality is when you put the knob over the top, it completely shields the holes that you've got underneath. So the neater ways to do that, perhaps the slightly easier ways to do that, but it doesn't matter. They're just the 4 holes that you need to somehow insert into the overlay when you do it. Now, clearly that you need to cut that out, and it explains all that in the manual. Now, just for Dave, he asked how we go about doing it. There's the highly sophisticated tool. A pointed modelling knife is what I use. So you cut the drilling template out with a piece of sticky tape, stick it on the housing, making sure you align the holes. I've got alignment holes on each side, at the top and on the bottom, and sorry, on the left and the right, to make sure that the drill template you've got on either side actually aligns, so everything's nice and neat. You just go through, put a modelling knife or a pin or something like that, and just mark and score the housing, so that when you pull it all off, you've got the spots to drill, and then paying very close attention to the drill thing with looking at the imperial or the metric measures. You select your appropriate weapon and attack the thing as well. Now, I'm fairly confident that each of the items that come in the kit, because you can see they're in a sealed container, are all exactly the same. There was a slight variation between the diameter of a couple of things on the kit that I had and the subsequent one that came in. So the moral of the tale here is, and I'm not suggesting you necessarily do it with this one, but would be to, if ever you're in this situation, don't necessarily take a published drill template for gospel. Pull out a measurement and measure the diameter of the device you're actually going to fit to make sure it accurately is reflected in the drill template. So the position's accurate, the diameter may well vary, but I'm fairly confident that we won't have that issue as we put this together. And you can see here, this is the polyvericon sitting in the middle with those two little screws that I mentioned that hold the polyvericon up against the housing. This was the new instruction kit that you've got. You can see here, I can't make it any clearer than that, but that's what it looks like when you start. Okay, so you bring your first lead in through here, through the middle, around the back, create tap 1, that's 1 turn. Through the middle, out the back, wind, that's a 2-turn tap. And you keep working your way around the list. If you look at the manual here, you'll see I drew this up. There's a detailed description of how many winds you have between each of the taps. The thing that I found the best thing to do is get a pencil, 1, 2, through the tap, mark it off. So you mark it down the track so you don't lose track of where you are on the taps as you work your way down. That's the technique that I used, and it worked very well. And then last but not least, final assembly where we put it all together, mounting the components in the housing, measuring out, and I explain how to do that, the pieces of wire, tin them between in the area here, install them into the ATU, and then when you go to put the housing on top, the overlay on top, here's a double-sided tape in every bit of spare real estate you've got on the top. And then you simply stick the overlay down onto the unit, and then you, in this case here, we've only got one particular type of component that's actually got a screw to screw down and hold it on. But very often, the tech I show in the manual, I've got some examples of where I've used this overlay before. Very often, I find it a very effective technique. It looks pretty professional for what it is for a homemade piece of kit. You generally have 2 or 3 switches or dials or knobs that need to be screwed down and bolted to the chassis. They themselves hold the overlay down onto the chassis, and it works very well. You know, I indicated here that, and just looking at this section here in the middle, this is the solution that solves the problem with the knob on the polyvericon. There's an aluminum shaft. Yes, so this piece of metal here actually has a slot cut out of it so that it sits down over the shaft on the polyvericon, and you have an M3 screw which goes down and holds it down so that you actually get a good mechanical connection on the way through. And this is a 6.4 millimeter shaft, so that it can actually take a 1/4-inch knob for those that don't know how to buy a 6-inch one, a 6 mil one, and set it to a 6 mil knob. So this is actually a 1/4-inch diameter knob, and it sits over the 6.4 millimeter shaft, made of aluminum, sitting on top of the polyvericon. But it works well. It really does, and you can see here. So look, the point I want to make here. I'd like you to this is a challenging project mechanically, right? Make no bones about that. But if you sit back, relax, take your time, work your way methodically through it, it's a very enjoyable experience as you do, particularly when you get to sit back. Who's pocketed my little, right, oh yeah. Particularly when you get to sit back, you almost don't want to put it in the kit. You know, it's such a nice looking thing. You don't want to hide it away behind all that plastic. Take your time, build it in stages, check your work at each stage. It's not a race, and take pride in it and enjoy it when you actually get to use it, because you know it really does work very well, as hopefully you saw in that video.
Are we going to have be able to test it after it's done?
If you finish it on Saturday, yes, I'll go out physically. But I don't think we're going to finish it on Saturday. So the reason I'm going to a lot of this stuff is the reality is some people will take it home and have to finish it and work their way through. As you know, for those, there's only a couple of kits yet to be collected. They're $15. All 20 were reserved. Now, if somebody's in the audience they didn't get one, the reality is you can buy these off Amazon. They are about, well, they're on sale right now for about $16. I think can't read what they're down from. So they are about that sort of money, but you don't get all the extras. So if anybody's in that situation, I do have a small amount of extra knobs, which I'll have on Saturday. I don't think I brought them here, as well as some extra shafts. So if you want a couple to have at home for a future project or something, please grab them from me. Otherwise, if you're going to be buying one, it's going to cost you $6 in freight just to get a little knob here or something like that. You know, it's not the best way to do. As I said, all the documentation is available on this GitHub site here. I will put this presentation up on the Groups IO page for the club under the Buildathon project as we work our way forward. And for those that would like to, we're going to have a supported build session on Saturday, just as we did with the ADX, starting with breakfast next door at 8 o'clock. The build session will commence at 9, or once we move our way down from that. And there we have it. So that's the end of the formal side of the presentation. There we go. Thank you.